This is a short video about some basic properties of the derivative of a function. So it's kind of the usual setup for a lot of these videos I've been doing. Say you got an interval of real numbers. Say C is a point in that interval. And let's say you've got two functions, f and g. It looks like a y. That's a g, I promise, there. And let's say that both these functions have the domain, that's this interval I, and let's say both of these are differentiable at C. So what does that mean? That means that f prime and g prime make sense to talk about at the value g. All right, so what we want to look at is what if I make some new functions out of f and g? So like what are some new functions that we're used to making when we're given two? Well, for right now, we're going to stick to if I added them together. What if I was to multiply them? And what if I was to take the quotient f over g? And so what's the derivative of those new functions, and how do they relate to the derivative of f and the derivative of g? Oh, and then one more. What if I was to just take f and multiply it by some number like 7, or in my case, alpha here? What's the derivative of that new function? So what do we got? If alpha is a real number, then the derivative of the function alpha times f should just be alpha times the derivative of f. So that's like your constant multiple rule that you remember from Calculus 1. The next one, so the derivative of the sum, f plus g, so the derivative of that function should just be, what does it say on the right side? That's the sum of the derivatives. So if you're going to differentiate, sine of x plus cosine of x, you just differentiate each one of them separately is what this says. All right, so now we get to the trickier ones that aren't as intuitive, or intuitive is maybe a goofy word, that don't behave maybe as we might like them to for right now. The derivative of a product, this is, remember, the product rule from Calc 1. So the derivative of f times g should be f prime evaluated at c times g of c plus g prime evaluated at c times f of c. And the last one, if g is non-zero at this value c, then the derivative of the quotient f over g makes sense to talk about. And here we get the quotient rule. And how I always remembered it was it's low d high minus high d low all over low squared. If you've never heard that before, sorry. It helped me a lot when I was going through calculus. All right, so I'm not going to prove all four of these. I'll just do part C because it's fun. So part C, we're going to prove the product rule. Why does this hold? So let's assume I've got some number x that's in my interval, and I don't want x to actually be c. Because what are we going to do? We're going to look at that difference quotient, that limit. So we're going to take the limit as x goes to c of, again, I should have, remember this is like the slope of the secant line of this function fg, right? So for 2 points on the graph of fg, what we're going to do is we're going to remember drag those 2 points closer and closer to each other so that eventually it should spit out the slope of the tangent line. Again, that's kind of the idea of the derivative. Anyway, though, that's some of the geometry that you might be thinking of. It doesn't really help me too much with what the proof of this is. What are we going to do? The first thing we're going to do is, I know what the product of two functions is. That should just be the same thing as f times g in each case. And now is where the trick comes in. I want to split this up somehow. And the way I'm going to do it is I'm going to very sneakily add and subtract the same thing. I'm going to add 0 in a sneaky way. And what I'm going to add and subtract is in green here. It's the quantity f of c times g of x. So I'm going to add it and subtract it here. And the reason I'm going to do that is because now I'm going to group these together. And I see that a g of x can come out of those. And I'm going to group these two, and I see that an f of c can come out of those. And that's the next line. So I pulled g of x out of these, and what would you have left? You'd have that f of x minus f of c. That's pretty nifty. And what else did I just say? I said we'd pull this f of c off both of these terms, and you'd have g of x minus g of c there. Now what we'll do is we will use some of our limit laws, where I know that I could split this up into the limit of just this stuff over x minus c plus the limit of this stuff over x minus c. So I'm saying get rid of that fraction with a common denominator, split it into two pieces, and then distribute the limit. So again, this much here is just this much here, plus this much here is this stuff here. All right, so the last thing that I need to do, what do I know? The limit as x approaches c of g of x. What should that be? Well, g is differentiable at c, therefore g is continuous at c. So I can conclude that that should just be g of c. And I'm also using a limit law here. The limit of this product should just be the limit of the first one times the limit of the second one. So what I'm trying to get at, the limit of this quantity should be g of c times the limit of this fraction is f prime of c. Pretty cool. Similarly over here, f of c is constant, so it could like come in front of the limit if you wanted to, and then you just have limit of this, which of course is just g prime of c. So that's the last line. So really, again, the subtlety that I really needed was the fact that, remember, being differentiable at a point implies you're continuous at a point. Therefore, since g is differentiable at c, I know what this limit is. It's just g of c. That is another subtle point besides the trick in the proof above, which was to add and subtract that sneaky thing. So that's the proof of the product rule. Now, the last thing I want to talk about for this video is just maybe 3 common notations for the derivative that we'll use in these videos. Of course, there are others, and depending on which textbook you look at, it might be different, but here are 3 pretty common ones, and these are the ones that are mentioned in Bartle and Sherbert as well. So the first one, we've already seen it. If you've got a function f, f prime is a great one. Another one, though, that we maybe haven't seen as much is this kind of function notation itself. Like d is this function, you probably guessed it, stands for derivative. So I'm saying d of f, oops, I don't want to talk about that last one yet. And if you take a course in linear algebra, this one would be very useful because, and let me just go into that for a second, if I think about some of these rules with the derivative, right? So like, what's this say? Well, the derivative of a multiple of a function, that multiple just kind of doesn't matter. I multiply at the end, right? So I've got that constant multiple rule. So in other words, like the multiple can kind of come outside of the derivative. And what else do I see in the next line? The derivative of a sum is the sum of the derivative. In other words, I can split this between the two. If you've had a linear algebra class, maybe you remember that these two things together are trying to say that this operation of taking the derivative is linear. And so this notation here, it's suggesting that the derivative is some kind of a linear transformation. And we could get a little bit abstract and like, well, what's your vector space? Well, you tell me the vector space of functions from your interval to the real numbers. And so if it makes sense to talk about the derivative there. And so again, this is trying to emphasize that the derivative itself is some kind of a I'll say function, but some kind of a linear transformation. If you've seen some linear algebra, maybe you've made that connection, or maybe you've even seen that before. And the last one, though, this kind of Leibniz notation, df dx. This one's kind of nice because it also emphasizes like what is your variable you're differentiating with respect to. And this one's pretty common in like differential equations. This notation kind of has an upshot where it's just a symbol. I shouldn't be able to cancel stuff, right? Like if I multiply by dx, that really has no meaning. I shouldn't be able to do that. But what you see in like solving things that are called like separable equation, like that idea kind of leads somewhere. So that notation's kind of nice as well.